All right, so for those of you who are joining us, today we're going to be talking a bit about section 5.1. And that is what we call the area problem. Now, the area problem is pretty much just the following. You take a nice function on an interval a to b. Maybe it curves down a bit. Maybe it's just a nice smooth ride. But the important thing is that you have some function defined between a to b. What you want to find is the area of S, this shaded region. Now, the problem with trying to find this area, as we saw in class, is that it's really, really hard. There's no just simple geometric formula to find this area. So what we do to this shaded region is we decide to dice it up a bit. Basically, we chop it up into rectangles that we spread an equal width apart. Now, I know that some of these might look a bit thicker than other rectangles that I draw, but I'm not perfect and I don't have a ruler with me. So just take that these are the same width by my word. Let's say they're not drawn to scale, right? Then what happens is that to make these rectangles, what I'm going to need are points here that we call x1, x2, x3, dot, dot, dot. And we extend out to the last nth rectangle. Now, if you notice closely by this diagram, the right endpoint of the last rectangle is actually going to be your endpoint B. And the left endpoint of the first rectangle is actually A. These get labeled xn and x0 appropriately. Now, the way that you get rectangles out of this chop up is in the following manner. You take the right endpoint and you drag it up to the function f. Then you make a nice horizontal line and you pull it to the left and drop down. So you pull it up to the left endpoint and drop down to it. And you just keep on doing this for each rectangle. I start with the right endpoint here that I dragged up to the function, bring it to the right until it hits the left, drop down. I got another rectangle. I came here at this point, I moved on up to the function, we moved on over, we drop down, we get another rectangle. And I just keep on doing that process. Now, that being said, if you're watching this video, I doubt that you have issue with the construction itself. You probably get that, okay, yeah, we're taking rectangles. Sure, that's fine. But you just might be having trouble on how we get the lengths and widths of these. So delta x is what we label as width. All right. And let's talk about how we find this delta x. Well, I'm working over an interval a to b, right? So what am I chopping up to size? Or sorry, chopping down to size. So basically, the idea behind this is that I have a certain amount of rectangles here. Now in this picture, I could only fit about 8 on screen, but in general, I could have 10, 100, a million, a billion. I can just keep on going until I can't fit anything else in there, right? So suppose that I just take an arbitrary n rectangles, right? Then what I have is one width here, and then another width, and then another, so on and so forth. I get an n total widths because I have n rectangles. And they all have to add up to be the length of the interval. So think about it like this. I have delta x plus delta x, the same width for every single rectangle. I'm just adding them up. N times. And what they have to be equal to is this entire width. Now the width of the interval a to b, we know that explicitly. You just take the right endpoint minus the left. But I added these up n times, right? So it's the same thing as if I took n multiplied by delta x. And that should be equal to b minus a. So if you just divide both sides by n, the width of these rectangles is b minus a over n. I hope that's pretty clear. Now you may be wondering, okay, well, fine, that's how we get width. How do we get length? Well, remember what I said, every single rectangle, you get a right endpoint. And we got to generalize that formula. So say I go out to this ith rectangle, then I went 1, 2, 3, so on and so forth, until I hit the ith rectangle. Now you start at A, but then to get to x1, I just add one width. To get to x2, I would add 2 widths. x3, 3 widths. So the generalizing to xi, I go I widths. I is just an index in this context. Do not confuse this I that I'm writing here with the imaginary number. I in this instance is just indicating that we're indexing these items. Now, with these xi, they're how we get our lengths. So what I said was that I want to take these points on the right, drag them up to the function. What do you think dragging that up means in a mathematical sense? Well, it's just plugging in those points to the function. The question here is just, okay, well, I want to get this y value. I know that this is some vertical distance. And the vertical distance would essentially be the y coordinate that I have here. But that's just going to be f at the point I plug in for each of these. So over here, whatever this xi is, it would still be f at xi. You just take the point that we have, plug it into the function, will be here. Okay, well, then the y coordinate just dropping down is going to give you your length, because the y coordinate at the point at the bottom is just 0. So it's once more an idea of larger minus smaller. It's just that the smaller is 0. So now we had a quick refresher on how we get our lengths and widths. Let's actually try to put it into action. Going on to the next slide. So let's estimate the area under the function sine of x squared on, say, 0 to pi. Yeah, sure. Using 4 rectangles. With a problem like this, if you can do 4 rectangles, you can do 10. You can do 8. You can do 100. It would take a lot more time to do 100, but you could do 100. So if you get this problem down, then you are more than set for approximating areas. Now, the general idea of this is still just like that picture. We have a function, we want to chop it down to size, but now in the sense I'm only using 4 rectangles. So first things first, got to put that x there. To get our width, we know that it's equal to a ratio. We got to figure out what it means in this context. So how many rectangles am I using? 4. So basically, each of these 4 is going to have a common width. And when I add all those up, it should be equal to the length of the interval. If we sort of make that connection between with what we did on the previous slide, well, that should hint you that in this instance, I'm dividing by 4, and I'm taking the length of the interval up top. So the change in x, our delta x, is pi over 4. And that's going to be our common width of the rectangles. Now we're only going to have 4 endpoints, right? So really, instead of generalizing for xi, we could just find x1, x2, x3, and x4. Well, I mean, of course, x4 is just, pi, but we could find x1, 2, and 3. But just for those who are maybe a little bit interested, we know that the general formula for xi is that we start at the left endpoint of the entire interval, and I add I times the width. So this will be like pi I over 4. Basically, x1 is then just pi over 4. x2 is then 2 pi over 4. Well, that's just like pi over 2. x3 is then 3 pi over 4. And x4 is just pi. The 4's cancel. So we have our endpoints now. I'll give you a second to write these down. If you need more than this time, pause the video. Go into the next slide. Now we have to find our lengths. So really, that's just plugging in the f of xi to the function. Now, I hope you remember what that function f was, or at least have it written down. But if you don't, I have you. It was sine of x squared. So this is going to be sine of pi squared over 16. Now, with an approximation problem like this, a lot of the times you're not going to get exact figures. And so you'll round off to a certain amount of decimal places. On a test, I usually say 3, but if you gave me 4, 5, 2, I wouldn't be mad. The important thing is that you're giving more than just the integer value. Now, that being said, if I plug this into my calculator, and as a rule of thumb, take 3 decimal places to round off to, we get a nice 0.578. Got to round down. And that's going to be the width the length approximately of your first rectangle. F at the next endpoint is going to be sine of pi over 2 squared. Well, that's just pi squared over 4. Now, if this were just a nice regular pi, okay, well, I wouldn't have to resort to using the calculator because we know these exact values. But because this is a pi squared now, all right, got to bust out the handy calculator. And what you get, rounding off to 3 decimal places, is a nice 0.624. Now, if we do a nice f at x3, we put in a 3 pi over 4, square it, and we get the following. Now we just plug it into our calculator. And we get that this is approximately negative 0.668. So this is tying in a little bit to the current section that we're on, but this is fine. You don't have to have the function remaining positive on the entire interval. You would still be okay taking this value. It's just that our sum here can extend to negative values. And then last but not least, sine of pi squared is going to be approximately a negative 0.430. All right, great. Cool. We found our lengths. So R4 is going to be approximately equal to the width times the sum of these lengths. R4 is some terminology we discussed in class. Essentially, it's just what we say to be the sum of all areas of these 4 rectangles. And what we also saw is that instead of taking it term by term and do a length times width, we can factor out width entirely and just take the sum of the lengths. And so now I just plug in my approximations. I will just put there we go. That'll just make it a bit clearer. Now we just put in the approximations. And we do this all in our calculator. So we're going to take this 0.578. We're going to add the 0.624, subtract out the 0.668, subtract out the 0.43, multiply that by a nice pi over 4. And what you're going to get is that this is approximately 0.08, round off to the 3rd decimal place, and we'll get a 2. So very little area. But as we know, after talking about some of the future sections in our class, and mainly some things at the end of this section as well, all this means is that we had some positive area, but we also had some negative area, things that dip below the x-axis that we had to take care of. Totally fine. Our definition can expand for that. Now, the Rn that I mentioned earlier, it's defined as the following. It's the sum, f of xi times delta x. Geometrically, we have a width times length. So each term is the area of a rectangle, where the lengths are determined by the right endpoints, as we did in that graph, and the width is just uniformly the same for each term. So in fact, I wouldn't even have to necessarily put the delta x here. I could factor it out. Honestly, whatever method you like better is what you should be doing. Now, to keep it in something that is just more commonly seen, I'm going to treat Rn as the following. Now, to find Rn, for a given function, on a given interval, well, it looks like we need two things, f of xi and delta x. Now, the delta x is always easy. Remember, in this instance, Rn means that there are n rectangles. So I'm taking the length of the interval, splitting it up n times. Right? All right, so this is what our width would reduce to. Now, unlike the last problem, where I could have just essentially said, okay, well, I can explicitly find all four of my right endpoints and call it a day. I don't really have to generalize. For this problem, you have to generalize. You can't just stop at the first three or the first four, because we got to consider any stopped n. N could be a million, could be a trillion, it could be a sextillion, it could be a lot of things. So we got to keep it general. But we know that we start at 1 and we go to a distance, I widths. But then I found delta x over here. So I just replace and multiply, and this should be the formula to get our ith endpoint. Now, we can take these right endpoints and plug them into the function. So the function was e to the x squared. So I'm going to get e to something squared. What goes here? This term. All right, cool. So, yay. You know, we have the two things we need to make the sum. All that's left is saying what the sum is. So the general Rn then is going to be the sum from 1 to n of the f of xi and delta x, but f of xi is e to the 1 plus 4i over n squared, and the delta x is this nice 4 over n. And that's it. Nothing else to the problem. Do not try to evaluate this limit. Very tough. Now, that being said, what I just said should probably give you a tip off about what this next example is going to be. So this is really for those who are interested in a bit of a challenge. This isn't really something that I would really give on a test necessarily. It's more so something just to ponder about. So we're going to find A for the function f of x equals x on just a plain old 0 to 1. Now, if you remember correctly, a is equal to the limit of the Rn. So first things first, to even start off with this question, we have to find Rn. All right, well, width is always easy. Let's see if we can find that. All right, well, we know we're chopping it up into n pieces. I take the length of the interval. We get a nice 1 over n. For the xi, I start at 0. I go at I times delta x. So this is just I over n. Now, the function f of x is just x. So when I plug in I over n, I just get back I over n. This is the only function for which you're going to get that Rn is equal to xi times delta x. But a common pitfall that people run into is that they assume that Rn is always xi times delta x. Do not make that pitfall. Now, that being said, now we can actually find Rn. Well, I got the f of xi, and I got the delta x. Now, to find the limit, I'm going to simplify things a bit. So what I'll note here is that if I multiply these two fractions, I have I over n squared. Now the denominator here of n squared, it doesn't depend on I. So what that means is that you can essentially treat it as a constant and factor it out of the sum. Then what would be left in our sum is just I summed up from 1 to n. Now, this might be something that just eludes some of us, but a finite sum formula that you can get is that if you sum up these I from 1 to n, then it's equivalent to the following ratio. Mainly, if I take the numbers 1, 2, 3, 4, 5, add them all up all the way to n, okay, well, it's the same thing as if I multiply n times n plus 1 and then divide by 2. So then I just start simplifying. And this will be the same thing as n plus 1 over 2n. Going to the next slide. A is equal to the limit as n tends to infinity on this Rn. We have the limit as n tends to infinity of then this n plus 1 over 2n. Now, if I take n to go to infinity on top, what do I get? A nice infinity. Same thing on the bottom. Infinity over infinity means that we have an indeterminate form. We can apply L'Hopital's rule to directly. Okay, well, derive the top with respect to n. And what you're going to get is the constant vanishes, but the n becomes 1. Derive the denominator by n, and what you're going to get is that the n vanishes, we just have the 2, our coefficient left. Now I'm just taking a limit on a constant. What should this be equal to? 1/2. And so what we have here is an example of where we can find exact area just using the definition of area with respect to that Rn. As we learned in 5.2, Rn is what we call a Riemann sum with right endpoints. But for now, all you really need to know is that Rn is the sum of n rectangles with right endpoints as far as their areas.